All right, hello everybody, and welcome to the final lesson in Chapter 0, and where I'm going to go over what we covered in Chapter 0, as well as a couple practice problems. I'm Lieutenant Timothy Mueller, and I'll be the instructor for this lesson. The first lesson, we talked about the center of gravity. We learned about how to model the center of gravity, how to model different systems, and calculate where the center of gravity was, and we saw it can be done horizontally and vertically. And we'll get to that in a little bit in the practice problem. You can also think of the center of gravity as a pivot point, and then we also talked about the moments around that pivot point. It's kind of like a seesaw. You want to balance that seesaw, and where it's balanced is going to be that center of gravity. If you have a seesaw and you put a weight on one side, in order to keep it balanced, you would have to shift that pivot point over towards that weight. If you remove that weight, so on this side, the pivot point would have to shift over because now there's more moments, or rather there's less moments on this side, so you have to shift the pivot point over in order to balance out your counterclockwise and clockwise moments. When you're talking about in the vertical sense, it's the same thing. If you put a weight up high, your center of gravity has to shift up high. Putting weight down low has to shift down low. Center of gravity and where it is, like I mentioned, is something that's extremely important to knowing at all times if you're a damage control assistant, engineer officer, or the commanding officer of a ship. Now, where the center of gravity is a single point where all the forces of gravity pushing down can be modeled as acting through, the center of buoyancy, as we learned, is the single point where all the forces acting up can be modeled pointing through. The center of buoyancy is just the centroid of the submerged volume of our ship. And we know that a ship immersed in a fluid, such as salt water or fresh water, has a buoyant force acting up against gravity upon it. We learned a little bit about writing moments in this lesson. We also learned about centroids of very basic shapes. In the practice problem we're going to have today, I'm going to go in depth on centroids of shapes and how to calculate the center of buoyancy. Now, this is something that's going to be a little bit out of the scope of what we need for this course. However, it's important to see how the math works so you see how the center of buoyancy shifts around as ships incline to one side or another. In our third lesson, we talked about calculating volumes of compartments, which as on ships, they're typically rectangular, so length times the breadth times the depth of seawater, or if it's completely flooded, the height of that compartment, as well as the densities of salt water, fresh water, and diesel fuel. These are common maritime liquids that we will deal with very often when we're talking about changing liquid loads on a ship. We learned that salt water is the most dense of all the three, with fresh water being second, and then diesel fuel being the least dense. We looked at this difference between density and specific volume, as well as we saw how to calculate the added weight or the removed weight from liquid if we know how much volume we took out of it and the specific volume. And finally, the last lesson was on ship nomenclature. Like I mentioned, it's very important for everyone that's involved in evolution to know exactly what's being mentioned. So teaching everyone proper ship nomenclature will definitely help you out in the future when you have evolution briefings or actual casualties, knowing exactly what to do and having everyone on the same page. All right, so let's just dive right into the first problem, and this is going to center on the center of gravity. So our first problem is going to be this prompt right here. So the first thing you have to do is take all the numbers that you have and do some housekeeping. You got to organize it. Let's put it into a table. So over here, we have a ship whose original displacement was 8,000 long tons with a kg at 19 feet. That means the center of gravity of the ship was 19 feet away from the keel. We unloaded some ammo, 250 long tons at 31 feet, as well as some stores, 75 long tons at 10 feet. We also removed some potable water. So instead of adding this weight, which is a positive value, we have a negative value, negative 10 long tons, and the center of gravity of that was at 20 feet. Now, when you compute your center of gravity, you can either do it through the equation method, which I've rewritten up here, r equals 1 over m, r being the coordinate of the center of gravity, m being the total mass, times the summation of each individual mass or force times each individual coordinate. Or I'm going to show you how to do it the moment way. I'm going to give you a little bit of time so you can fill out this table on your own. You're going to put all the displacements of all the items. We have the indexes right here. You're going to put the kgs, and then you're going to calculate the moments. And the moment is just going to be your displacement times the kg of that individual item. All right, so hopefully you were able to figure out that table and get something just like what I have to the right of the screen. All the displacements are just in the same order as we had originally in the prompt, as well as the kgs. Our moments are just the displacement times the kg. So the ship itself exerts a moment of 152,000 foot long tons. The ammo, 750. The stores on load is 750. And then the loss of the potable water reduces the moment by 200. We have to find our capital M. No matter what we do, we always have to find the total mass of the system. So we just add all the displacements together, and we get 8,315 long tons. Now we can solve our equation. We have all the moments, which we know we just add them all together. This is all the individual M1, M2, M3, and so forth, times each individual lowercase r1, lowercase r2, lowercase r3. You get all these moments, you add them all together, you divide it by your total mass, the total mass of the system, and then you'll get the r coordinate, which is, in our case, our kg. All right, now as you saw from that screen, you should have had a final displacement of 8,315 long tons and then a final kg of 19.28 feet. That makes sense. We had a ship that had an original kg of 19. We added a lot of ammo up high with the missiles, so we had a very strong moment moving us up that way. We also added some stores down low, which was going to shift that center of gravity down a little bit because of that influence, but not as much as the ammo. And then we removed some potable water from a little bit higher than where that 19 was. That was at 20 feet. So with all that center of gravity moving around, all we have to do is just add up all the moments together. Then we divide by the total mass of the system, or the total weight, and then we get our answer. So right here, final displacement is 8315 with a kg final of 19.28. Let's take a look at that from the moment perspective of a balancing beam. Here I've just redrawn our system with the pivot point at the kg, 19.28. We had an addition of 75 long tons at 10 feet. That was the dry stores. We have an addition of 8,000 long tons at 19. That's the ship itself. We have the removal of weight. So instead of pointing down, or instead of pushing down, it's actually pushing up. And that's the potable water that we lost, 20 feet, negative 10 long tons. Then we have the added ammo, which was 250 long tons and 31 feet. Now I'll leave it up to you to do this on your own to calculate the moments about the center of gravity. Remember, it's 19.28. So you just take the distance from 19.28 to each arrow, and then you multiply it by that weight, and you should see that everything that's trying to make it go clockwise is counteracting everything that's trying to make it go counterclockwise. Let's see, this is trying to make it go counterclockwise, this is trying to make it go counterclockwise, this is trying to make it go counterclockwise, and this is trying to make it go clockwise. So do the math for yourself and see if everything checks out. All right, next up for problem 2, we're going to be talking about the center of buoyancy and how to find the center of buoyancy on a very simple shaped hull. So here's the prompt for the question. All right, so what do we have? We have this barge here. It's got a center of gravity, a waterline, and then a center of buoyancy. We know that it rotates at the waterline along the center line. So if we draw a point right here, that is where the barge will rotate about. We're looking at a 10-degree roll here, giving a beam of 20 feet. Now we have to find the x-coordinate and the y-coordinate of the center of buoyancy. Well, just intuitively, We know that the center of buoyancy, if we roll this way, okay, so this side will be low, the starboard side will be lower than the port side. We know that we're going to have more submerged volume on our right side, which means that center of buoyancy is going to shift over to the right. It's also going to go up a little bit because we're going to be losing a little wedge of buoyancy here and gaining a little bit here. And if you don't remember that, you can go back to lesson 2 and just kind of refresh yourself on that. All right, cool. So we start here with just another rendition of this. Starting here, 20-foot beam, 3.5 feet to the waterline, and then we end here. And so instead of drawing the barge over to the side, I'm just going to draw the waterline around the barge. We have this relatively complex shape. However, if you break it down into the basic shapes that we had talked about earlier in lesson 2, it's actually not that difficult. So we have a triangle here, we have a triangle here, and we're going to see that they're exactly the same triangle. We have a rectangle here, which is really easy to find the center of buoyancy of, and a rectangle here, which is also really easy to find the center of buoyancy of. When you're trying to find the center of buoyancy, it's just like trying to find the center of gravity. However, in gravity, you're using either mass or a force. When you're trying to find centroids, you're using the area. So we're going to be taking moments of area over the total area rather than moments of force divided by the total force. So where we had foot long tons divided by long tons, now we're just going to have foot times foot squared divided by feet squared. Now, the most difficult part of this problem is going to be finding out this triangle. We got to find a side that we don't know about, and we also have to find an area. Breaking this down to the simpler shapes, two triangles, a rectangle here and a rectangle here, we know that it's easy to find the center of buoyancy of a rectangle. It's just half the height and half the width. So 2 should be pretty easy. We know that it goes from all the way from one side to the center line. So that's just going to be halfway through there, but we don't know this height. We also don't know this height of this triangle either. However, we do know that this is 3.5. And we'll see later here in a second that we do have enough information to find everything about this triangle and thus this shape number 2 rectangle. And that's all over there. But for number 3, we know that it goes from the axis of rotation all the way down to the keel. We know that's 3.5 feet. We also know it goes all the way from the center line of the ship to the end. So we know that's 10 feet. So we have everything that we need to solve for shape number 3. So now let's move into shape number 1, this triangle. It's a right triangle by definition, and we're just inclined over 10 degrees. Now I've drawn the center of buoyancy in the approximate location it's going to be. We learned in lesson 2 that for a right triangle, the center of buoyancy is going to be 2/3 away from the point. So in the horizontal aspect, here's the point, and here's the large end. Center of buoyancy is going to be 2/3 away from the point. It's also, you can say, 1/3 away from the big end. So in the vertical aspect, we have the point here, and we have the big end here. It's going to be 1/3 away from the big end. So now we know the bottom, we know the x length of that triangle, so we can find the x-coordinate of our center of buoyancy. It's just 6.67. Now we have to find that y-coordinate. And I've already saw a coordinate written here, however we're going to go through the steps underneath. If you go back to regular trigonometry, well, we know we have to find the height of this side. And to do so, given an angle and one of the sides of the triangle, we can just use basic trigonometry. If you remember SOHCAHTOA, sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and the one we're going to use is the tangent equals opposite over adjacent. So the tangent of an angle, we know the angle because we're inclined over 10 degrees. Tangent's just a function, so now we know the tangent of 10 equals opposite s, because s is opposite of the 10-degree angle, over 10. 10 is the adjacent side to the 10-degree angle. Then this is a hypotenuse, which we're not going to be using right now. So setting up our equation, we have one equation, one unknown, so we can solve for the s. We find that s equals 1.763 feet. Cool. We can use that over here. We know that this height here is 1.763 feet. We know the entire length of this is 3.5 feet. So we can subtract 1.763 from 3.5 and we can get the height of this rectangle. We know that it's 10 feet wide, and now we know how high it is. So now we have 2 figured out and 3 figured out. We have 1 figured out, and 4 is exactly the same as 1. So everything that has to do with 1 is exactly the same in 4. So when you, like I said, when you're doing centroids, you have to know coordinates and your area. So each individual part here, instead of being the forces like we had talked about in center of gravity, is going to be these shapes. Each shape has an x and a y coordinate of its center of buoyancy, as well as its own area. So we have to take the area of the triangle, which is 1/2 of the base times height, and we're going to get 8.816 feet. So we have x equals 6.67, y equals 1/3 up of 1.763, which is 0.587, and the area is 8.816. Now we got the 2 triangles out of the way, all we have left are the 2 rectangles, and we know those are pretty easy to solve. So let's take a look at number 2. I've redrawn how the shape configuration is here to match the notes that I have. So number 2 is going to be all the way from one side to the other. So it's going to be the entire beam, or 20 feet. The height is going to be 3.5 minus that side that we figured out for the triangle, which is going to be 1.737. We know that x is half of the width, so this is going to be 10. We know that y is just half of the height, which is going to be 0.868. Area is length times height, so for this rectangle, it's going to be 35.74 square feet. Number 3 is very simple as well. The height is just going to be the height of the triangle that we figured out, and the length, or the width, is going to be 10. It's half the beam. So the x is going to be half of 10, which is 5. Y is going to be half of 1.763, which is 0.881. And then the area is going to be 17.63, which is just 1.763 times 10. All right, now the next step is to take the actual configuration of the shapes and get our actual x and actual y measurements. We found x and y for each individual shape in relation to themselves. However, that's not in relation to the entire system. So here's our system right now, kind of chopped up into these different shapes. We have the center of buoyancy of 2 is just halfway in and halfway up its height. However, the center of buoyancy of 1, while its x coordinate is what we had calculated at 6.66, the y is the height of 2 plus the y coordinate of 1. Similarly for 3, its x coordinate is the length of the triangle, which we know is 10, plus the x coordinate that we found for 3, which was 5. So that would make the x coordinate for 3 here 15. There's a difference between its own x and y and then the x and y within the system. So we know that this is 10. We know that this here is 6.66 or 6.67. We know that this here is 15. Now we have 4. For the x coordinate is going to be 10, which is the beam, plus 2/3 of 10, which is the x coordinate that we had found for the triangle itself, which is going to be 10 plus 6.67, which is going to give us 16.67. Now take the same ideals and do them for y. So we already know the height for 2. We know the y for 2. We know the height of this rectangle. And we know the y for this first triangle here, number 1. We know the height of the rectangle. We also know the y coordinate for 3. And we know the height of this rectangle. We know the height of this rectangle. And we also know the y coordinate for the triangle. Now organize them into each shape. So now, where you had a table with each individual shape's x and y, now put it in terms of the system. So now you have shape 1 with its own system x and y and area, shape 2 with its own x and y and area, and the areas of these shapes aren't going to change. 3, x, y, and area, as well as 4, x, y, and area. Now we're just going to do exactly the same thing that I mentioned before. We're going to take the moments of area divided by the total area, and the total area is just the adding up the area of the two triangles and the two rectangles. And we're going to find the x-coordinate and the y-coordinate of the center of buoyancy of the system overall. And that's going to be the centroid of that entire shape. So the centroid of an entire shape, the centroid of an entire system, is just the same concept as the center of gravity. It's the summation of each individual shape's area times each individual shape's coordinate, whether that's in the horizontal or the vertical direction, and then divided by the total area of that system. And then if you were using horizontal coordinates for each individual component, that will give you the horizontal component of the center of buoyancy of the entire system. All right, that was definitely a difficult way to do things. And you're not going to be expected to know how to calculate the center of buoyancy in DCASE class. However, it's always good to know how these things work, how these relationships work, and see the mathematics behind how things change, such as in here, the center of buoyancy is going to move to the, or in this case, it went to the right, and it went up a little bit, as you probably saw. It's swinging through that arc that I had mentioned before, has a center called the metacenter. And we'll get into that in chapter 1. However, now you're kind of thinking about, okay, that center of buoyancy is going to shift a little bit. Now we're going to learn a little bit about the metacenter, and you already have some inside knowledge and mathematical knowledge behind how it moves. All right, now to kind of round out this video, we're going to talk about lesson 1, center of gravity, as well as lesson 3, which had the specific volumes in it. We're going to talk about if we have a fuel tank, we're going to fill it up from 7 to 95%, and we're going to see how far the center of gravity is going to shift due to that weight addition. So here's the prompt for the question. All right, now what do we have? We know that we have this 3 TAC 150 TAC 1 TAC Foxtrot, a fuel tank, that is going from 7% full to 95% full. We know that our initial displacement of the ship is 7,500 long tons, and the interior bulkhead, BH's bulkhead, is 20 feet off the center line of the ship. So to draw it, we want to find how far does the center of gravity move in the horizontal direction, or GX. So here we have the center line of the ship, right over here. The interior bulkhead is 20 feet away. Then we were given the dimensions of this fuel tank. We're going to assume it's completely rectangle or rectangular, 17 feet high, 10 in width, and 23 in length. All right, so now we know we're talking about center of gravity. So we have to think, how many long tons are we going to be putting into this tank? We know we go from one condition to another condition, so we have to find out how many are added to the tank, not how many there are in the very end. Then we have to just think about, all right, I have a center of gravity that's assumed to be perfectly centerline on the ship. Now I'm going to be shifting over, I'm going to be adding a moment, and I also have to divide by the total mass of the system. So I have to find the amount of weight added, add that to the original weight of the ship. Then I have to kind of think about, okay, I have a ship, but the center of gravity is on the center line, so the distance is going to be 0. So I can just say, I don't even have to worry about the center of gravity of the ship or anything like that. I can just take the long tons of fuel that I added, I can take how far away that center of gravity is, and then divide by the total weight of the entire ship with that added fuel, and that's going to tell me how far the center of gravity is going to move. So there's not as many steps to this as there was in previous center of gravity problems. So let's start taking a look at it. So at 7% full, we have to find out how high that is, since the length and width of the compartment aren't going to be changing as we fill the tank, only the height's going to be changing. So when we're at 7% full, where is that height going to be? From that height, we can calculate the volume, then we can calculate the total long tons that there are originally. So we have the height, if we take 7%, so we're just taking 17 feet, and we're multiplying it by 7%, or 0.07, getting 1.19, and say, okay, now I have a height of 1.19, I know 10, and I know 23, so I can get a total volume of 273.7 cubic feet. And now if we take that volume, big V with the horizontal bar, divided by the specific volume of diesel fuel, which we know is 43 cubic feet per long ton, we can get our long tons, which is just a hair under 6.4 long tons. Now let's go into the after condition, where we're at 95% full. The exact same steps apply. We have to find that height, then we calculate our volume, divide by specific volume, and we get our displacement. Height is going to be 16.15. Calculate your volume. It's going to be right a little bit above 3,700 cubic feet. And then your final displacement, that should be 0. Your final displacement is going to be 86.384 or 86.384 long tons. Now we have to find the amount of weight that was added. Okay. So the amount added is going to be the final minus the original. And this is the original. So we have 86.384 minus 6.365. And that's going to be just over 80 long tons. So we're adding 80 long tons. Now we have to find where is that center of gravity. If we're looking in the horizontal direction, we don't worry about the length because that's in the longitudinal direction. We're just thinking transverse direction, or X. So this center of gravity is going to be right here. It's going to be a rectangle, and no matter how high that center or that waterline is, the center of gravity is always going to remain in the same spot. It's just going to be rising up or down, but we're only concerned about horizontally right now. So we know it's 20 over, and we always have a rectangle or a square. But we know that no matter if it's a rectangle or a square, that center of gravity is always going to be right in the middle of the extremes. So we have a width of 10, which means our center of gravity is going to be 5. So adding 5 to 20, we're going to get 25. So now we know we've added 80.019 long tons, 25 feet over. Now we have everything we need to know. We have 80 long tons times 25, and then we're going to divide it by the final displacement. To get the final displacement, we take what our ship was originally, 7,500, and we have to add to that what was added, which is 80.019. Now that you've seen how center of gravity, center of buoyancy, specific volumes, and ship's nomenclature are all important in damage control and making sure that a ship is seaworthy and is able to fight damage, we're going to conclude Chapter 0 right now. And in further chapters, we're going to get more into the weeds of center of gravity. We're going to talk about the metacenter a lot more, metacentric height, trim, list, all these things that I kind of touched on in Chapter 0. We're going to go much more in depth. We're going to look at mathematics behind it, deriving where it comes from, and seeing how center of gravity, center of buoyancy, metacenter, how they all change. So you can kind of look really quickly at your ship and say, okay, I'm becoming more stable or less stable. But like I said, I'm going to conclude Chapter 0 right now. I'm Lieutenant Timothy Mueller, and I hope you have a great day.